Okay, can you guys hear me again? Okay, good. Are there, let me just spend a few more minutes going over briefly this PCA one more time, given that it's new to a lot of you. So we write page, let's see, 17. So you have your data, xn, this is in RD, n is equal to 1 up to n. So in the example, d was equal to 4, n was equal to, I think, 13. Then you center it. So center it. So that means you take the average of your x's and you subtract it away. So maybe you should call this x and tilde, and then you just subtract away the mean of it. This is going to be your x's, just so we don't have any mean. Otherwise, you would have to worry about the intercept on, and so I don't want to do that. So you center it, and then you form the covariance. This was the S. This was 1 over n minus 1. And then you have your x n t, and you can see here without centering it, the covariance would you have to subtract away the mean here. And so that's why I'm doing it this way. And again, this one here, this is a d by 1, and this one here, this is then going to be a 1 by d. Right, so overall, this becomes a d by d. And then you write out S as you write out S in terms of its eigenvectors and eigenvalues. The notation we used was V D V T, where your V would be, this would be these eigen vectors B1, B2 up to BD. And D would be lambda 1, lambda D, and then there'll be zeros. And so what you're interested in is you're interested in looking at the norm of xn minus its approximation, xn star. Maybe you want to sum here, you want to sum over and then do this normalization, same normalization as the one we have up here. So what that becomes is 1 over n minus 1, the sum over n's, and then the norm. Depending on how well approximation you're using, you will get you'll get a sum from, what did we have? D equals m plus 1 to d, and then there was this xn transpose together with the eigenvector be D, everything squared. We could write this one here out in terms of the variance covariance matrix. The S up here, you could write this here out as 1 over. So this is when you absorb it. You absorb the factor here into the matrix S, and we will write this here as the sum from D equals n plus 1 to D, and then this would be B D transpose, and then you have the variance covariance matrix, and then B D. And so what we looked at was having D here to be an eigenvector. Right? So then when S is applied to an eigenvector, you're going to get the eigenvalue times itself. And then what you'll get here is this is a constant, right? So, and here you'll just have BD transpose BD, this is equal to 1. You'll end up here with the sum of the eigenvalues. Right, so for example, so for m equal to 0, then we'll just get that the error is equal to all the eigenvalues. And in our example, this was adding up these 4 eigenvalues would give us everything, and then you could do an estimate for the case where you project down to a 0-dimensional space, then you will get an error. That would just be the last one. So this will be lambda 2 plus lambda 3 plus lambda d, and then you can see how it goes. The more terms you include, for m equal to d, then the error is 0. So that's what we saw in the example. We saw how this error moves depending upon the size of the subspace that you're projecting on. Are there any questions about what we've done so far? You guys are very quiet today. Keep in mind, I am not a mind reader, in particular using Zoom. If there are any questions or comments about what we've been doing today, it's a good time to do it. You're, of course, also welcome to use office hours. I got an email from your TA. He wants to double check regarding his office hours if he needs to move them to a different time. He has them on Thursday and Friday nights, and he wants to make sure that you guys have at least an opportunity to attend one of them. So if you could, please reply to him if this is not working for you. So again, my office hours are tomorrow morning, and his are tonight and tomorrow night. Cool. Alice is saying something. Yeah, so that's a good question. So the let me write that down again. Right, so we have a matrix, let's call it S, and our dimensions for this would be d by d. So this is a matrix, right? It's equal to right there. So here we'll have, that's this D here. That's that D. Right, and the first D is this one here. That's this one there. Right, so I can write S applied to a vector, say B. This works, provided, so again, this here is a D by D. And this here is, this is a D by 1. Okay, so why am I so careful about writing this out? So let me tell you a story about why is it that I'm kind of fixated on trying to get these dimensions right. Okay, so years ago, this was before the financial crisis. So this was in 2004 or 2005. This was when credit derivatives, they were taking off in the US. And this is how I ended up moving to the US in the first place. It was to teach a course on credit derivatives. So this was in 2003, 2004, so 15 years ago. And I was teaching this course on credit derivatives, and we ended up playing with like a Cholesky factorization of some sort. And I missed a transpose. I put a transpose in the wrong place. And this was probably the first or second class that I taught this. And I was doing notes like this, actually on a document camera, because even back in those days, we were teaching on document cameras at Carnegie Mellon. So it was exactly a setting like this one, running on a document camera, and you're going through it, and there's a transpose missing in one of my formulas. The amount of work that this one missing transpose ultimately led to, because everything that you do when you write code subsequently, if it's missing that one transpose, it won't work. When you're writing down this Cholesky factorization, it really matters whether you write A times AT or you write AT times A. This stuff is not the same, right? So let me just highlight this. Let me just highlight this by looking at one of the formulas where something like this could make a huge difference. Right here, we had this AZ, right? So we're taking independent normals and we're multiplying onto this Cholesky factorization. If I would put a T here instead, or if I would move this matrix to the other side and put a T over here, this stuff here, it's going to change. So it matters tremendously whenever you're working with matrices, whether you transpose them or you do not transpose them. So I'm trying to be a bit careful when I'm writing this stuff out. And one way I find that it helps is to keep track of these dimensions, right? So if I take a D by D times a D by 1, the inner ones cancel, and the overall here is going to be a D by 1. Right, so whenever I write on the right-hand side, it better have the form D by 1. So I take a matrix, a D by D, and I take a vector, a D by 1. This is going to give me a D by 1, right? So whatever I write over here, it has to be a D by 1. And this property here, this is the eigen, vector and eigen value property. That means that if I take S and apply it to B, I get B back. B indeed is a D by 1, but it's only up to some scalar. So this is my lambda. The eigenvector, this is B, and the eigenvalue, this is going to be my lambda. And what I want to do is, I very often want my vector here to have length 1. Right, so this norm here, this is equal to, like my B is going to be, like my B is going to be B1, B2, BD. Right, so the norm of a vector is equal to b1 squared plus b2 squared plus bd squared. And then if I want the norm, I have to take the square root, so this is why I put the square here. So I want this to be equal to 1. This is just a normalization. It's when you're talking about, so in R2, if I have a vector b, I'm just restricting it to be in the unit circle of length 1, right? So I'm just taking something here that points out like that. And so I can, if I am in R2, what this here allows me to do is if I take a general x, I can of course write my general x. This is going to be x1 over x2. I can write this as x1 times the usual basis element, that's this guy. So this is 1, 0 plus x2. And then the other one is this one up here, 0, 1. But I can write it in many other ways. I can also write this here as a beta 1 times say b1 plus beta 2 times b2. Right, but these two are orthogonal, and these are my loadings. And very often you will see these bases, the basis of a d-dimensional space being expressed in terms of these eigenvectors that have been normalized to have length 1. Right, so this here is what it means to be an eigenvector. I take the matrix, I multiply it onto B, and I get B back up to some scalar. That's the definition of an eigenvector and an eigenvalue. Does that make sense, Alice? Yeah, it's a bit of linear algebra. It is. Yeah, but sometimes when you see theory, and it can be pretty abstract, but when you apply it to a specific problem, it becomes much less abstract. Are there other questions or comments? So one thing that you can encounter, so one problem you can often encounter with data. And this is why I was a bit surprised. This was why I was a bit surprised when I saw that example that that we looked at before, when I showed you the example here in Hull. That example in there, Hull had an example with 10. So one thing that you often encounter with data is, for my experience has been like for D bigger than 6, D bigger than 7, you get eigenvalues you get some eigenvalues that are equal to 0. And this is why I'm really surprised that he could go all the way up to 10. My experience is that when you get to around 6 or 7, so then that matrix, that S is singular, right? Because the determinant of S this is just what is the product? The product of these eigenvalues, right? This is, so it becomes 0. So in this case, there are, so looking back at what we've done, right? This means that there are directions, there are bases, there are bases, or I should say there are eigenvectors which explain nothing. And this is probably not completely correct. So what that means is that when you're estimating this matrix here, this really is an estimate. And yeah. In other words, this matrix here, S, was given to be, this is semi-definite. I can't even spell it, definite. But it can be singular. Right, so semi-definite, this is going to give you that your lambda is a positive, but it can be singular. So you can have that there are 0 eigenvalues. Right? If it were to be a positive definite, this is just a node, so S is positive. So this is positive, semi-definite, so it's positive, definite, and then your lambda is now positive. And what I'm saying is that if you have data in high dimensions, so you're trying to compress, and Hall says he can do it in dimension 10. I'm more like, my experience has been like 6 or 7 is when my code starts falling apart. Then the way that I estimate it, and you get these eigenvectors out, they start becoming close to 0. Lee is asking, are you talking about 6 and 7? Yeah, so that's just my impression. So one place where you will see this is so if you looked at Markovich, how do you spell Markovich? Let's see. I'm not very good with spelling these names, and I want to get them right in case you guys want to look up. More information about it. Just look up Markovich is the right way to spell Markovich. How is Markovich not mentioned in here? So Markovich is, in many ways, he's the father of a lot of things in quant finance. He got his thesis years ago, and to a large extent, he was. Markovich has an interesting story. If you don't know Markovich, his claim to fame, according to himself, I saw a talk, so I'm just going to write Markovich. I think this is how you spell it. Markovich, he was the one that he did a PhD, and according to himself, when he gave so he got the Nobel Prize, and he's been touring around more recent years. I mean, I'm not even sure if he's alive yet, but what has it been, like 10 years since I saw him give a talk, developing software partially based upon his PhD thesis from decades ago. So he's the one that brought covariance into quantitative finance, right? So he was the one that realized that the covariance, this is important for what we're doing. So Markovich, he says this is like mean variance trading. So what you look at is you plot the mean, so this is the expected return, and then you plot, is it variance or is it standard deviation now? This is either, it's probably standard deviation. This is not how you spell deviation. This is the square root of variance. Okay, so you have your stock, and you plot their variances and you plot their expected returns, and you plot them in here in this picture, and you get all this stuff. So we have like 1, 2, 3, 4, 5, there are like 11 here. So there are 11 stocks, and then you form the mean variance frontier. You form the mean variance frontier. So this is typically something that looks like this. This is Markovich, right? So what you want to do is, and maybe there's a risk-free return you can trade in here. Maybe there's a non-zero intercept. So there's an asset that doesn't have any risk associated to it. And so the efficient frontier is going to be, you go from here and then you go up to here, and then you go around like that. Right? So that's the efficient frontier. This is where all investors, that's what you're gonna hold. Right? You're gonna be somewhere up on this line. You don't want to be in here, because for the same variance, you can get a higher expected return. So you're going to be pushing up on this efficient frontier. This one here, this is called the tangent portfolio. And if you are interested in something called CAPM is one way of CAPM is to say that the tangent is equal to the market portfolio. Anyway, the market portfolio is just, you look at these capitalizations, how much does each stock weigh in the overall picture. But that's a different point. But what you will be interested in looking at creating is this efficient frontier here. Right? So you want to create points. You want to create all these points up here on the top line. And to do that, you need, surprise, surprise, you need the covariance matrix. And this is what Markovich realized. Right, so to create the efficient frontier, you need the variance, the covariance matrix between all the stocks. Between the 11 stocks returns. And as you can see, this is in reality, but you have many more here, right? If you had 110, you would have to have 110 here. And so if you start estimating the covariance between 110 stocks, and so here is my point, is that when you get up to 6 or 7 stocks, you get singularity. This is my experience. This is just experience. This is my experience. We used to teach this stuff here to our students. Have you seen this mean variance analysis in other classes? Has anybody seen this mean variance analysis? Amy has seen it in the finance class. Mission has seen it. Lee has seen the CAB-M. Yeah, okay. But this is another place where you need to find the variance covariance matrix and to create this efficient frontier up here. And yeah, so and then this is I have seen when we taught this stuff years ago, we would have the students figure out, like, of course it depends on what data you're looking at, it depends on what stocks you're looking at and so on, but in general it's hard to go past 10. Like these eigenvalues, they really drop. And yeah. And this one here is like in a typical finance course, you will see stuff like this early on. Okay, I think we're almost out of time. We still need to clean up a little bit this exception rejection algorithm. We didn't get to it, and this is something you need for your homework. When is the first homework due? Homework 1 is due. Okay, so I think I'm going to push the homework a little bit because we didn't get to talk about the acceptance rejection algorithm. We only have a few minutes. I think we're even out of time. Yeah, so I'll push the homework a little bit so we have time to do this acceptance rejection algorithm. And next time we'll start with that. Okay, are there any other questions or comments, or? We good? Okay, so if you could reply to the TA about office hours, if they are, if you want a different slot, and otherwise I'll have office hours tomorrow morning, and I'll push the homework back another week, and so we can finish up the acceptance rejection algorithm. This PCA analysis took a little bit longer than I had expected. All right, I will see you guys hopefully tomorrow, or I'll see you guys next week.